Okay, so we're going to finish up section 6.3 today. And so then we'll continue on with the other sections of 7 on Monday, and we should be able to that done. That being said, I have moved the due date for the homework for chapter 7 to Wednesday at midnight. And so this is the end of our, that's at the day of our review. And so that you'll be able to finish that up and have it reviewed for our exam next Friday. Remember, don't come to Zoom on Friday, just log into Top Hat and go ahead and do the exam on next Friday. Okay, but we do have a class, Zoom class on Monday and Wednesday. Okay, so that being said, are there any questions related to what's due this week or what's due next week? Okay. So if you do have questions, go ahead and either chime in or put them in the chat and I will answer them as I can. So let's go ahead and start with our, continue with our chapter 6.3, which is all about SN1 reactions and how to tell the difference between an SN1 reaction and an SN2 reaction. Okay, so the first thing we learned about an SN1 reaction is that it has at least 2 humps in our reaction coordinate diagram. The reason is that we have an actual intermediate in our species. Our actual intermediate is our carbocation. So that means that we have to form a carbocation in this step. And because of that, that means that, sorry, I need to mute my watch apparently. Oh, it is muted. That's weird. Okay. We have to form that intermediate first, which means that we need to stabilize that carbocation. And we have a couple different ways of doing that. So we want to look at how to stabilize that carbocation, when those carbocations form, and how we can use that to our advantage to make different reactions than our SN1. There is no group activity today. It will be on Wednesday of next week. Okay. So the general mechanism of this was the first step, we formed our carbocation. Now the next step, we can use a very poor nucleophile to attack our carbocation because the carbocation is already charged. So we can actually use poor nucleophiles, uncharged nucleophiles, to do the next step of the reaction. And in this case, we're using water, which means we're forming our second intermediate, which is our protonated alcohol. Okay, so that means in this case, we actually have to have a third step happen. That third step happens to be the deprotonation of the alcohol to give us our final uncharged organic product. Okay, so that are the 3 steps associated with the SN1 mechanism if you're attacking with a neutral species. If you're attacking with an anion species, then we have a positive charge and a negative charge. And when those electrons form that new bond, we have a neutral species. So we only have 2 steps in a reaction where we have a charged nucleophile. So let's go and look at that mechanism again. Okay, so if we form a carbocation, right? That carbocation is sp2 hybridized trigonal planar with a p orbital above and below the plane. Okay, that means that our nucleophile can come in and donate its electrons to the p orbital at the top or the other part of the p orbital at the bottom. So what this means is if we have an SN1 reaction, we end up with a mixture of products because the nucleophile can come from the top or the bottom, messing up any stereochemistry you may have had, okay? So in this example here, we actually have an optically active hexane here with the bromine on it. The bromine's gonna leave first, giving us our carbocation. Our carbocation then is gonna be trigonal planar, and our water can come in and attack from the top of that, giving 1 isomer, and in this case, it would be giving this R isomer. See where the OH is exactly where the bromine would be. So the OH is gonna attack at the top of that carbocation, giving us that R isomer. However, if it came to the bottom isomer, it's going to invert the rest of it and it turns into the S isomer here. Okay, so why, let's see, actually, no, yeah, I'm sorry. It comes in from the top giving us a S isomer and it comes in from the bottom giving our R isomer. They flipped the molecules around at the bottom. Okay, so In an SN1 reaction, we always get inversion of center. If it was R, it's now S. If it was S, it's now R. In an SN1 reaction, we get a mixture. So we end up with what we call a racemic mixture, or an equal mixture of the R and the S, and therefore it cancels each other out, so it no longer is optically active. Okay. So that being said, whenever we look at a reaction, we can actually measure the optical activity at the end. If we started with an optically active species and we wanted to know whether we were doing an SN1 or an SN2 reaction, we could just measure the optical activity at the end. If the material is optically active at the end of the reaction, that means it must have gone through an SN2 reaction and inverted that stereocenter. Okay. If we started with something that was optically active and it turns to be optically inactive, or a 50-50 mixture of the two different isomers, then we know we had to go through an SN1 reaction. We formed that carbocation and the nucleophile attacked equally on the top and the bottom, giving us that racemic mixture, or 50-50 mixture of the two different isomers. So that makes this reaction not stereospecific. Okay, the SN2 reaction is stereospecific because it gives us inversion of stereocenter. The SN1 reaction is not stereospecific because it gives us a mixture of isomers. Okay. So what things help stabilize our SN1 reactions? Okay. So the first thing that really helps stabilize an SN1 reaction is to stabilize that carbocation intermediate. And the best way to stabilize this carbocation intermediate is to use a solvent that promotes that carbocation. So in the case of the reaction, the first thing that happens is that we can have that solvent act as the nucleophile. Okay, so as the solvent's neutral, and as long as it has a lone pair on it, it can act as a nucleophile. So our first reaction we want to talk about is what we call solvolysis. And in solvolysis, we basically don't add a nucleophile, we only add the solvent, and the solvent becomes the nucleophile after you form the carbocation. So in the case of solvolysis here, we can use anything with a lone pair. And in this case here, we have water, ethanol, and in this case, we have formic acid. So it's a carboxylic acid that only has a hydrogen on it, so the methyl group. Okay, so in each of these cases, notice they are all protic solvents. They all have hydrogen bondable hydrogens on them. Okay, this is key to an SN1 reaction. Most SN1 reactions work better when we have a polar protic solvent, because that polar protic solvent helps stabilize that carbocation. So if we don't add any other nucleophile to the system, the lone pair on the water, the lone pair on the alcohol, and the lone pair on the carboxylic acid oxygen can react with that carbocation when it's formed. And when it does, it has to then lose a proton, and we generate our, in this case, an alcohol because we used water. In this case, we generate an ether because we used an alcohol that already had a carbon chain on it. And so now we have a carbon-oxygen-carbon bond. And in this case, we actually form an ester. Okay, so we formed our carboxylic acid is now bound to the carbon that had the carbocation, and we formed an ester. Okay, so that's if we don't add a nucleophile. But what if we do add a nucleophile? When we do add nucleophiles, we can actually add very weak nucleophiles because we already formed our positive charge. Okay, so the next thing we need to think about is, why do protic solvents help SN1 reactions? Okay, so in the first step of our SN1 reaction, we have to break a bond. Okay, there's like 5 or 6 things that happen in a mechanism, and one of those is to break a bond, forming stable charged species. Okay, in this case here, we're breaking the bond between the carbon and the leaving group, because usually the leaving group is a very electronegative atom and can leave as an ion, an anion in particular. So let's say we have this compound, and it barely dissolves in water as a hydrocarbon with a leaving group on it. And let's say we start to polarize that bond. As we polarize that bond, the water can use the positive sides, or the hydrogen bonding tips, to stabilize the negative charge. Okay, so that will stabilize the anion and make it dissolve into solution. And then it is partially, part of that charge is compensated for by the solvent. Okay, then as we do this, our organic portion here flattens out, gives us that sp3 hybridized trigonal planar, and it has a positive charge now. And the lone pairs on the water can act as the stabilizer for that positive charge. Okay, so just the formation of the carbocation is promoted by the use of the polar protic solvent. Okay, so how does that look in the energy diagram? Well, as it turns out, because the polar protic solvents can stabilize that breaking of the bond, that makes the activation energy of breaking that bond smaller. Okay, so because it's smaller, that's going to promote the reaction. In an SN1 reaction, we are a unimolecular reaction, right? So we have two humps. But that also means it only depends on the concentration of the organic substrate with the leaving group on it. Okay, so that means that first activation energy is the slow step and the one we want to control. Okay, so in the case of forming that carbocation, if it's easy to polarize that bond with our protic solvent, then it decreases the energy state. So for example, if we did the same substrate and we did it in methanol, right here, a polar protic solvent, and we did this one in acetone, a polar aprotic solvent, the reaction would actually progress much faster, or if it's not hot enough, this one might not even progress at all because it doesn't have enough energy to reach that transition state first. Now, once you form that transition state, notice even the energy in the transition state is lower in the polar protic solvent because it's stabilizing that positive charge. Here we have a charge and we only have dipole interactions with our solvent to do it. We have hydrogen bonding helping stabilize that charge. We only have polar dipole interactions to stabilize this charge. So even the intermediate is more stable in those polar protic solvents. Okay, and then of course, when they cascade back down, they'll cascade back down to the same product. Okay, so just to give you an idea of the relative rates of these things, let's just take this bromo T-butyl bromide right here and run the reaction in water. And so we're going to do a solvolysis. We basically are going to add water to the thing to create T-butyl alcohol. Okay, and it's going to create a little bit of HBr in the one equivalent of HBr in the system as well. Okay, so if we do this in water, its relative rate is 400,000 times faster than if we did that same reaction in acetone. Okay, so in this case here, for every 1 molecule of water, you have 9 molecules of acetone, approximately. And so the acetone's doing the job of creating that solvent shell around that substrate. Acetone can only do dipolar interactions and therefore makes the intermediate less stable and makes the activation energy much higher. Therefore, that much higher rate is literally one time it will react when in the other solvent, it goes 400,000 times. Okay, so that's the general, that is a dramatic representation of how the polar protic solvent promotes an SN1 reaction and why we always use polar protic solvents in our SN1 reactions. Okay, all right, so some differences to note here is that the SN1 has to have that carbocation. So the SN1 mechanism needs that polar solvent to be used. In an SN2 reaction, we typically use polar aprotic solvents to increase the rate, okay? Because we don't want that competition of the hydrogen bonding interacting with our nucleophile. If our solvent is adding protons to our nucleophile, it makes it less of a nucleophile. Therefore, it slows the reaction down. So SN2 reactions use aprotic solvents. SN1 reaction uses protic solvents. Now, That doesn't mean an SN2 reaction won't occur in a protic solvent, because it still has nucleophiles in there, but it's going to slow it down because those nucleophiles can be protonated part of the time. Okay. In contrast, SN1 reactions react very slowly, if at all, in aprotic solvents, because the inability to form the carbocation at a reasonable temperature and a reasonable rate. Okay, so let's talk about the different solvents and the different relative rates. Okay, so we have solvents, and the first set of solvents we have here are what we call polar protic solvents, water and alcohols, right? The second set of solvent we have here is a polar aprotic solvent, and then these two are kind of not polar, okay? So this E right here, E is dielectric constant, okay? So it's an epsilon, but it's a dielectric constant. And dielectric constant is basically a measure of how polar a compound is, okay? So the higher the polarity, the higher the number. So if we look at our water, ethanol, and methanol here, we all have dielectric constants above 20, okay? Now, let's look at the relative rates. At the lowest polarity we have in ethanol, because the hydrogen bonding group has some extra carbons and hydrogens to carry in the solution, so it's lowering that polarity. It goes at a relative rate of about 200 times, okay? And then just by switching to a more polar solvent, that jumps by 5 times. And going to water, which is the most polar, one of the more polar, acetic acid is also very polar like that. It jumps another 8 times, okay? So that means water, this reaction with the t-butyl chloride is 40 times faster in water than it is in ethanol. So when you, and then you'll explore that in lab at some point in time, I think. Okay, now let's look at something that has similar polarity. So the acetone and the ethanol have similar polarity, but ethanol can hydrogen bond, okay? Acetone can't hydrogen bond, okay? And it's 200 times slower, okay? Just that loss of that proton, that loss of that protic solvent decreases the rate again. And then when we get to these last two solvents here, the dielectric constants are very low. They are not very polar at all. Even though we have lone pairs here to try to help stabilize things, it still slows the reaction down. And in hexane, we only have van der Waals forces or induced dipole forces. So the reaction pretty much just shuts down and we don't see anything happen in that reaction. So this is the power of the polar protic solvents in the mechanism of the SN1 reaction. Okay. So let's look at an overview of the two, okay? SN2 reaction, if we looked at the coordinate diagram, it happens in one step, okay? Substrate, nucleophile, boom, leaving group leaves. Reaction's done. So we have one step, and it all depends on the concentration of both the substrate and the nucleophile, okay? Because they have to be in the same place at the same time to make the reaction happen. Okay. Now, there is a slight difference in the activation energy between the polar aprotic solvent and the polar protic solvent, because if the polar protic solvent is protonating your nucleophile, then it has to wait around for a non-protonated nucleophile to get to that transition state. So there is a slight difference in there, but it is noticeable. So our polar aprotic solvents are the ones we want to use for our SN2 reaction, but our polar protic solvents will work also. Okay. So let's see. And in our SN2 reactions, we want to have a negative charge or at least a partially negative charge. The negative charge or partially negative charge makes it a better nucleophile and therefore works faster. Okay. In an SN1, the first step is the breaking of a bond to form a cation. Okay. So now we don't have to have a full negative charge on our nucleophile because we have a full positive charge on our substrate. So that means we can have a neutral molecule come in and form our new sigma bond. Okay. Now notice that again, the first step is forming this intermediate, this carbocation here. Okay. So the energy barrier to get to the carbocation is lower in polar protic solvents, okay, and is higher in polar aprotic solvents. So there's a significant difference in rate in the SN1 reaction. So when we do SN1 reactions, look for, you can use neutral poor nucleophiles, but you must use a polar protic solvent, okay, to form that carbocation. Okay, so if forming that carbocation is important, we need to talk about the stability of carbocations at some point. Okay, so let's look at the different substrates we can use for these SN1 reactions. Okay, and in general, the tertiary the tertiary substrates react faster than the secondary substrates, which react much, much faster than the primary substrates, and methyl substrates hardly ever react at all in an SN1 reaction, okay? And it has everything to do with carbocation stability, okay? So if we look up here, our methyl cation here is the least stable. That charge is not shareable with any of the groups. The hydrogens are about the same electronegativity, and they're using all their electrons to make that same bond, okay? If we put one carbon here, we can draw a little bit of electron density away from that carbon to help stabilize that positive charge. Once we get to a secondary, we can do that with both of the groups attached to it, making our tertiary the most stable of our non-double bonded systems, because we can donate electron density into all three systems. Okay. All three of those carbons can donate, making it the most stable. So carbocation stability is directly related to SN1 reaction rate. Okay. So is there a way to better stabilize one of these cations here? And the only other way we have to stabilize a cation is through resonance, okay? So this is all inductively and hyperconjugation. We're sharing through the bonds, we're sharing with the hydrogens next to this carbon. But in the case of where we can move electrons back and forth, now we have part of a positive charge here and part of a positive charge here. So that's even more stable than our tertiary carbocations. And when we have the ability to have a leaving group that leaves on the CH2 on a benzene ring, we again gain stability of the system because we can share that positive charge with the benzene ring. So that makes these two right here even more stable, which makes them more react faster than even our tertiary carbocation here. Okay. So let's look into a little bit about that. Okay. So the things that are happening to help stabilize our carbocations in at least the resonance here has everything to do with the idea that we're just flipping electrons back and forth right here, and therefore we're sharing that positive charge over those two sites, okay? So we have one positive charge shared over two sites, so that's going to be more stable than one charge on one site. Okay. However, in the carbocation, the tertiary carbocation, we do not have resonance, okay? We have an inductive effect where these are pulling from the electron density of the carbons around it, but also there's a thing called hyperconjugation. Okay. In hyperconjugation, when we have a methyl group that's next to the carbocation here, we have a sigma bond to hydrogen. So we have the ability of that sp3 hybridized sigma bond giving a little bit of through space donation, and that's called hyperconjugation. It's not full conjugation, because in full conjugation, you need a p orbital next to a p orbital. But because we have some electron density and they're close enough in space, it can donate a little bit of its electron density through space, okay? And it has, it can only do one being, only one of the hydrogens on each of the methyl groups can do this, because only one can be aligned with the empty p orbital. So if you only have one hydrogen stabilizing it, that's why your mono substituted is more stable than your methyl cation because it has no hyperconjugation and it has nothing to pull, nowhere to pull in an extra electron density. In the case of your tertiary here, it can hyperconjugate with this one, it can hyperconjugate with one of the hydrogens here, and it can hyperconjugate with one of the hydrogens here, making it the most stable of the system. Okay, so what does that mean? Okay, so because of that, we have a relative stability and a relative way how we can look at SN1 reactions. Okay, so our tertiary and secondary alkyl halides are more stabilized because of hyperconjugation, and therefore they are faster than the methyl and the primary. In fact, for the most part, the methyl and the primary do not react in an SN1 conditions. If they do react, it's so slow, it's not a useful reaction. Okay, so whenever we have a methyl halide or a primary, we tend to not use any kind of SN1 reaction because it just doesn't work very well. Now, so if we have our secondary and tertiary substrates, that means they are going to work because of that stabilization. However, if we have resonance helping us out, these are even going to be faster. Okay. And that relative rate has a lot to do with that activation energy. Because this cation is more stable, it has a lower activation energy. Taking away one of those carbons and only allowing hyperconjugation with two methyls increases the activation energy. And then taking away another one increases that activation energy again until we get to here. So by the time we get to these two here, our activation energy is above what we can do with just regular heat in our reaction mechanisms. Okay. So, but there are some limitations. You might think that, oh, well, the vinyl group might work really well, or just substitution on a benzene will work well. But that's not true. It has to be allylic. We have to have that extra thing for conjugation. Because if we just took vinyl bromide, it doesn't form a cation here because we're trying to put a positive charge in an sp2 hybridized orbital. We already have a p orbital activated here. We already have our sigma bond here and a sigma bond here. So we will not form the carbocation on vinyl systems or on benzenes either. Benzenes only undergo a substitution reaction. They do not undergo this kind of formation of a positive charge. Okay, so if the number of substituents on that carbocation affects the rate, why? Okay, it has everything to do with the idea that the Hammond postulate suggests that the closer the transition state is to the products, the easier it is to get there. Okay, so in the case here, our transition state happens to be the breaking of a bond, giving us a partially positive carbon and a partially negative leaving group. Okay, so because of this breaking is closer to what our products would look like. It actually lowers the activation energy. It lowers the Gibbs free energy, giving us a exergonic reaction. I'm sorry, endergonic reaction. Okay. So one of the problems we have when we have carbocations is that if you form a secondary carbocation, it wants to be a tertiary carbocation. Carbocations, the tertiaries are much, much more stable. Therefore, it wants to be one. So if it can convert from a secondary carbocation to a tertiary carbocation, it will. And it actually has two different ways to do that. And the two different ways to do that are what we call a hydride migration or a proton shift. It's not a proton shift. It's a hydride migration, and I'll tell you why. And then we also have a methyl shift. This only happens one bond. So it's called a 1,2 hydride shift or a 1,2 methyl shift. Okay, so let's look at the methyl one first. So the idea is that both of the electrons in the sigma bond are going to migrate over to the secondary carbocation. And when they do that, the carbon it was on turns into a tertiary carbocation. Okay. This only goes from secondary to tertiary. It will never go tertiary to tertiary. It'll never go secondary to secondary. It only goes secondary to tertiary. Okay. Now, so we can move a methyl group that way to give us our tertiary carbocation. But then the next one is what we call a hydride migration. Okay. The reason we call it a hydride migration, not a proton migration, is it's actually going to take the electrons with it. Okay. So when we have a hydrogen with 2 electrons on it, filling that s orbital, we call that a hydride. It's a negatively charged hydrogen. Okay. So it's going to take those 2 electrons with it to shift over, and in this case, giving us our tertiary carbocation. Okay. So that's one thing that can happen a lot in our SN1 reactions. Once you form that carbocation, you have to see, is there the possibility of moving that carbocation 1 carbon over, and only 1 carbon over, to give it a more stable carbocation. And the whole idea here is that we're just, looking at the hyperconjugation associated with it. Because think about it, this, in the case of our hyperconjugation, it's using that sp3 hybridized orbital. Those electrons there are going to be pulled over and transitioned to our positive charge here to generate our tertiary carbocation. And once we form our tertiary carbocation, all 3 of the substituents can add to the hyperconjugation stability of that carbocation. All right, so let's look at what carbocation rearrangements look like. Okay, so from an energy diagram perspective, we get to our first transition state because it was a secondary carbocation, so it's a kind of a high transition state energy, giving us to our tertiary, our secondary carbocation. And then we have to have a little bit of activation energy. You've got to, have a little bit of energy in there to get it to break a bond, to shift those electrons over. And so there's a little bit of a transition state energy, but then it really is much more stable as that tertiary carbocation. And then of course we have this last little bit of energy that's moving your species against electron-electron repulsion to get into the correct position to form our new sigma bond. That's that activation energy here, which gives us our final products. Okay, so in this case here, we have a tertiary carbon here. We have a secondary carbon here with a leaving group on it. Okay, first step is the formation of the breaking of that bond with the leaving group, giving us our secondary carbocation. Then spontaneously, it's going to rearrange, giving us our tertiary carbocation fairly quickly. So it will be your major product in the reaction. And then the nucleophile can come in and attack at the top or the bottom to give us our final product here. Okay. And so that's what a carbocation looks like, carbocation rearrangement. So it only goes from a secondary to a tertiary, but there's another driving force that can make carbocations rearrange. And that can be done in the example of a ring. Okay, so let's look at this first example here, though. So in the case of this, we're using a acid catalyzed reaction with an alcohol. Okay, so I'm actually running this in lab this week, so that's kind of fun. And so the first thing we have to do is we have to make our OH a good leaving group. So we protonate it. So now we have a protonated alcohol, and now it's a good leaving group, so it can leave. And so when it leaves, it forms our carbocation, and then our nucleophile can come in and react to that carbocation, giving us our product. Okay. So, but in the case of this here, it's actually showing it moving from a secondary to a secondary. That very rarely happens, so I'm not going to do that example because that's not what happens. And let's go to our second example here with a ring. Okay, carbocation rearrangements in rings can be driven by the fact that, number one, you're going from a secondary to a tertiary, but when you have small rings smaller, like 5, 4, and 3-membered rings, you also have ring strain. You also have those bonds are not at 109 degrees, and so they have energy that wants them to expand. Okay, so whenever you have a carbocation formed adjacent to a small ring, there is an opportunity for that ring to expand and give us our tertiary carbocation. Okay, so this is technically a methyl shift because we're taking this carbon here and we're taking these electrons and moving them into this direction. Okay, but the first step is the same. We're protonating our alcohol. Our alcohol then that is now protonated and it can leave as water, giving us our secondary carbocation. And then our secondary carbocation wants to rearrange to our tertiary carbocation. Now, this is the hard part, making sure that we are moving these electrons over here and keeping track of where our substituents are. Okay, so notice we now have a 5-membered ring, and we have our methyl group that didn't move, and we have this group right here, which is at the end of the chain where the ethyl group was, to give us our newly expanded ring. And now that we have our newly expanded ring, we can have our nucleophile come in and give us our final product. Okay. So that's the only problem with SN1 reactions besides the loss of stereochemistry. So we have the loss of stereochemistry and we have the possibility for a carbocation rearrangement. Okay. But we can make really nice things like tertiary alkyl halides, and we can make tertiary alcohols from this system, where that would be more difficult to do it in an SN2 type reaction. Okay. So the Hammond postulate suggests that because an SN2 reaction, the transition state looks more like the starting materials, that it is going to relate to having an early transition state, and therefore it's going to give us an exothermic reaction. Okay, in the case of an SN1, because the transition state looks almost like the products right here, it tends to be an endothermic reaction as well. So that is one thing to look for in the way these systems are, is that our SN2 looks much more like the starting materials, our SN1 looks much more like the products. Okay, so how can we tell if things are happening? Okay, when do we know that an SN1 is going to happen? Well, first thing we want to look at is what type of halide we have. So if we have a methyl halide or a primary halide, the answer is no. An SN1 reaction is not going to happen, or it's going to react so slowly that we don't see it. Okay. Now, if we have a tertiary or secondary halide, then we could form an SN1 type reaction, but are we going to do an SN2 reaction? In a tertiary system, we now have sterics blocking us. It's slowing down that SN2 reaction because we can't get that second molecule in there. Therefore, our SN1 reaction is more likely to occur on our tertiary alkyl halides. Okay, so just looking at the type of halide we have, we can really discern at least methyl and primary halides versus tertiary halides. Okay, but where do we go if we have something like a secondary? Okay, well, when you have a secondary system, and this is basically the same argument here, when you have a secondary system, we have to think a little bit deeper. Okay, so since the tertiary halides only do SN1 and methyls and primaries only do SN2, where does secondaries fit in here? Okay, so we have to dig a little deeper. We can't just say, oh, it's a secondary, it must do blah. Okay, when we have secondaries, we have to look at the solvent. Okay, if it's in a polar aprotic solvent, it's probably going to go SN2. If it's in a polar protic solvent, it's probably going to go SN1. Okay, leaving group. Is it a good leaving group? Okay, so is it something like a halide, or is it a protonable alcohol? Does it leave as a neutral species, or does it leave as a very stable ion? Okay, so that's very important for this. If you have a poorer leaving group, like a fluoride ion, it doesn't want to leave, so we probably won't go in SN1 reaction. And then we look at the nucleophile, okay? In the case of an SN1 reaction, we can actually deal with very poor nucleophiles, neutral species, and it will still progress. In an SN2 reaction, if we have a poor nucleophile, it's going to react very slowly, okay? So the idea is we want a very good leaving group, a protonated water, a big fluffy halogen like a bromine or an iodine. We want a very poor nucleophile, something that's neutral or is very low on that nucleophilic extinction, and we want a polar protic solvent. Okay. So we have to look at our solvent and our nucleophile to determine if it's going to go SN1 or SN2. Now, if you have a good nucleophile, something that has a negative charge, if you have a polar aprotic solvent, and your leaving group is not necessarily really good, you're probably going to go under an SN2 reaction. Okay, so let's say you have a chloride ion, you're doing it in acetone, and you're attacking it with a large concentration of iodine. Okay, iodine's a pretty good nucleophile, and it has a non-protic solvent, and it has chlorine, which is not a great leaving group. It's going to go SN2. Okay, so the net result of all of that is this little table here, right here. So when you see your tertiary alkyl halide or your tertiary group with a leaving group, it's not going to go out under SN2. Steric interaction, it's going to go SN1. Okay. When you have your primary methyl, it's not going to go SN1 because you can't form the carbocation. It's only going to go SN2 because there's very little sterics. In the case of your group here, we look at leaving group, sterics, solvent, nucleophile. And if you compare and contrast those four things, you can tell whether or not it's going to be an SN1 reaction or an SN2 reaction. First thing I would do is look at the solvent, because that you cannot do your SN1 reaction without your polar protic solvent. Okay, so the number two, the secondary, is the one that's going to give you the most trouble, but start looking at those four factors and you will be able to discern SN1 versus SN2 on secondary substrates. Okay, so let's say you want to know how to do this, right? Okay, let's first of all add any lone pairs to all the atoms. Now, the reason we want to do that is we want to see where are the lone pairs, what is partially positive, partially negative, and that tells us if something's going to have a reactive site or not. Next thing you want to do is you want to identify the nucleophile or the electrophile. Okay, so the nucleophile is going to probably be the one with the lone pairs or a negative charge. The electrophile is the one that has a polarized bond, making usually the carbon partially positive. Okay, you want to look at the electrophile. Okay, how stable would that electrophile be if it formed a carbocation? If it would be pretty stable as a carbocation, then we might start tilting our way toward the carbocation formation. Is the solvent protic or not protic? Okay, protic favors SN1. This should be enough information to get you to decide between the two, okay? And again, most of the time, the secondary is the one you have to go through each and every one of these steps. And then the next thing you do is you use arrows to illustrate the mechanism of this bond. So the net overall on this is that by racking and stacking in our head, what are bases, what are nucleophiles, what is strong, and what is weak, we can get an idea of how things are going to react. Okay, so the first thing we want to look at is our weak bases that are good nucleophiles. So good nucleophiles are negatively charged. Our weak bases are those that their conjugate acids are very strong. Okay, so look at it that way. So that gives us an idea that, you know, these two halides and sulfur and this carbon anion and this nitrogen anion are good nucleophiles, but weak bases. So the next thing we go up is, okay, what would be weak bases but are not necessarily as good, okay? Now in the case of this, we have a less stabilized negative charge and not as acidic as these, so it's still a weak base. Here we have a delocalized negative charge, a delocalized negative charge, and a delocalized negative charge because of conjugation, right? That's why they're weaker nucleophiles, okay? And they're not, and if we protonated them, they would be fairly acidic, okay? The next thing we go is to what we call our strong bases, okay? Hydroxide and alkoxides, always a strong base. And they're good nucleophiles because they have negative charges. But when we have strong bases, we have to worry about elimination reactions. Specifically, E2 elimination reactions. Now, what if we have a strong base that's bulky, okay? If it gets too big, it can't come in and act as a nucleophile. Therefore, they become poor nucleophiles. And we start looking at elimination reactions instead. And then our last thing we have are weak bases and poor nucleophiles. In the case of weak bases or poor nucleophiles, that means they have to undergo SN1 because they are not strong enough to form that new bond themselves. They have to wait for that positive charge to form on carbon before it can happen. Okay, all right. Questions on SN1 versus SN2. Okay, so it should be fairly easy to rack and stack the tertiaries and the methyls and the primaries. And I gave you a strategy for looking at what you should look for in a secondary. Okay. All right, so this is going to tie in very well with the activity that I'll be sending out on next Wednesday. It's basically a group of practice problems where I have, let me pull up the introduction to that. No, I don't have it here, darn it. So on the slide, I have some introduction about a table to use to help you guide you through the system. And let me see if I can pull it up over here, actually. It's a very good table. Activity. All right, let me go ahead and pull this one up. I'm going to stop sharing. This will come out with the activity, but it is also will help you with your SN1, SN2, E1, E2 homework. So basically, we're looking at what kinds of acids and bases we have. We just covered that in the last half of this module right here. What makes a strong base a strong base? What makes a weak base a weak base? And so that's what this is going to be. And then I have this table here, okay? Using this reminder of what strong acids and bases are, right here, and looking at the reagents we're using here, what the different groups are going to do. And what you can see here is that, like the methyl, is only going to do SN2 reactions, okay? The primary is only going to do SN2 reactions or E2 reactions. The secondary can do all four mechanisms, and we just have to know whether we have a strong base, a weak base, a good nucleophile, or a solvent that promotes it. And then our tertiaries only undergo E2 reactions with strong bases and SN1, and a competition between SN1 and E1 in weak bases. Okay, so then that'll be our practice that we'll do on Wednesday. All right, questions for this chapter? Okay, if you don't have any questions, go ahead and head off to your next class. If you do have questions, hang back. I'm going to stop recording so that I hopefully will be able to hear you.